Hi, next I'd like just to mention the local central limit theorem, which I'm not going to prove either. Local central limit theorem. So the setup is the same, almost. Let xi be iid. For simplicity, I'm taking the mean 0. You can always subtract the mean if that's not the case. And finite variance, of course, which I call sigma square. Okay. I'm also going to assume that xi have absolute continuous. Xi's are absolute continuous, so they have a density. Xi's are absolutely continuous, and they have actually a bounded density. With bounded density. Okay, so density doesn't blow up. Then the limit n goes to infinity of, so what do we want to do? What do we want to look at? It's a local central limit theorem. So if I look at the rescaled sum of the iid random variables, so divide by standard deviation of the sum, it's mean 0, so I don't have to subtract the mean, and I take the distribution function at a point x. Now what I want to talk about is a local CLT. So what I'm going to do with this is differentiate it to get something like a density. In fact, it is going to be the density of the rescaled sum Sn, and then this density should be close to standard normal density, which is 1 over root 2 pi e to the minus x squared over 2. So it's a local CLT talking about densities. Densities are close to each other. If I look at the difference of this, then even if I take the worst case in x, it still goes to 0 as n goes to infinity. That's the local central limit theorem. If you remember the Demois of Laplace, the way we proved the Demois of Laplace using combinatorial arguments actually provided us with the local central limit theorem. So that can be generalized with some work, which I'm not going to do here, and that's one version of that local central limit theorem.